Welcome everybody to today's SimScale webinar on cloud-native simulation and physics AI applications for the home appliances and light industrial equipment industries. My name is Alex and I'll be your host for today's session, and I'm very excited to be joined by speakers from SimScale and also from Nantu, who are an innovative company building consumer goods for caring for green spaces. I think this is going to be a very informative and interesting session, so let's get started. Please do enter any questions that you have in the Q&A panel as we go along. We will have time to address those at the end. Now, before we begin, I will briefly introduce today's speakers. So the first voice you will hear after mine will be Alex Fisher, who's a co-founder and product manager at SimScale. Today, he leads the company's work on thermal management and electronic solutions, and he will start us off with a brief introduction to SimScale. After that, we will hear from Nantu. We have two speakers, starting with Beatrice Sileno, who is CEO and founder, and will introduce us to Nantu and to the Biocycle project that we'll be looking at today. And she'll be followed by Andrea Torino, Chief R&D Engineer at Nantu, and he will take us on a technical deep dive into exactly how SimScale is used to optimize the design. And then finally, he will return to Alex to explore how physics AI models can help to accelerate this kind of product development, and he will give us a short demo with SimScale. So it's time to get into it. Alex, are you ready to start?
Thank you, Alex. Yes, I am. Great. So then I'll give you really, as Alex said, a brief introduction to SimScale. I will keep it short so that we can dive fast into the great product and applications from Nantu, but just that you get a quick overview. So for the ones who do not know SimScale, we are a company that provides CAE services and simulations. We have over 600 users worldwide, 600,000 users worldwide, and over customers in over 50 countries. We have a lot of academic institutions using SimScale as well, both in education, but also in the academic research. And we have millions of simulations in production on our cloud-based system. That is interesting later on when I will be speaking about unlocking the AI in engineering, as obviously this data that is hosted by us is quite helpful there as well. We have over 130 employees across 8+ time zones. Also important for us, as we are quite proud of our support. I'll also tell you a bit more about that in a second. What we do is SimScale empowers engineering teams to innovate faster. So in different industries, among them the most trending ones right now, electrification, energy transition, but also net zero cities, sustainable topics around engineering, a perfect match for today's topic. Obviously, we are trying to make the transformations happen that are underway and be really a great partner for other engineering teams that are really challenging the status quo. So trying to get the simulation lead times down, to make it possible to do design-based simulation-driven and enable optimization and other models like AI or surrogate models to really speed up development and optimize engineering. How SimScale works is that it's simply a cloud-native simulation platform that helps us essentially to do our support quite differently, what you saw also on the previous slide. So we can do real-time collaboration and support by just jumping onto projects together. So that means in your team, you can collaboratively work on one project, but you can also pull in our support. You can even give permissions like edit rights if you need help, and you get essentially help at the moment where a problem occurs and not via some ticketing system or days or weeks after. We can run simulations essentially at any scale. So that's perfect if you do parameterized simulations or you train data for AI, for example, as there are no limits in the sense of how many simulations you run in parallel. And obviously the cloud also provides a backend that allows us to scale to a high number, of course, and run simulations really efficiently. And we kind of combined a broad system of physics on our platform. So we have flow simulations, electromagnetic, thermal, structural combinations of these. So that makes it possible for companies to pick up one tool and do many different things and many different optimizations on SimScale. Additionally, I mentioned already that it's cloud-based and accessible via browser. So that is kind of the core of how our product works. That makes it really accessible to everyone around the world. You need just a simple web browser, no specific hardware or anything like that. But it also makes the data accessible for now, example, training AI models or the like. We try to be cost effective by allowing SimScale to be usable and productive for different sizes of teams. So if it's now one specific simulation engineer that does work, or if it's now a large team of hundreds of engineers that also have sometimes just on-demand use of simulation, we can be quite flexible by rolling it out essentially as single user seats on SimScale. And the main topic from our side today, the AI powered part, I already mentioned, right? So by storing the simulation accessible for AI training and other things, it's quite easy for us to be a forerunner in this trendy technology. Great, then a quick look out onto example applications that we have from the home appliance and gardening tools industry. So obviously there's a variety of products in this industry, and there's different applications that need to be looked at and optimized. So like today's pressure drop is important, flow rate, for example, for leaf blowers, but we also can provide electromagnetics and thermal support for induction cooking applications, rotating flow, wireless charging, just named here, freshness, so refrigeration systems, where it's often important to run a variety of simulations and then produce simplified thermal models, be it AI or be it reduced order models that allow you to potentially then deploy a very simple thermal model of your product on the product, kind of as a in live state. That can be done, and obviously structural simulations are possible as well, like in this case, a vibration example. That should already be it as a quick introduction to SimScale and what we are doing and how we are helping the home appliances industry. And now I will pass over so that we can directly get some great insights from our partners from Nantu, and will hand for that over the presentation to them.
Thank you, Alex, and hi, everybody. I am Beatrice Sileno, CEO and co-founder of Nantu, and I'm here to briefly share what we're building. Collecting leaves with current tools is incredibly inefficient. It's slow, messy, and frustrating. And every autumn, this monster of leaves returns, and no blower in the world seems strong enough to defeat it. Italy generates 2.3 million tons of green waste every year, and that's 15 times the volume of the Colosseum. That's why we created Nantu, the first integrated multi-accessory system. It delivers superior vacuum performance and reduces leaf volume by 19% directly into compostable bag, the leaf pods. So no mess, no waste contact, and it's ready for the circular economy. We switch between modes instantly, so no manual reconfiguration. And we have snap-on accessories for full versatility, so from leaf collection to complete outdoor cleaning. One system for a total outdoor cleaning. It's simple, smart, and sustainable. And turning an ambitious idea into a real scalable product was our biggest challenge. It started with a beautiful idea, but getting from vision to reality has been far tougher and more frustrating than I ever imagined. And every prototype came with a high price tag, long delays, and a constant echo of "this is impossible."
And here it comes the moment in which we needed a paradigm shift. So basically, thanks to SimScale, we could approach a different way of designing the machine, embracing the digital twin. Actually, our system is very, very simple if you think about that. It's basically a vacuum that also works as a blower, but in general, how does it work? Basically, it vacuums the leaves present on the ground floor by intaking the air. then the leaves get grinded and trapped into a compostable bag, as Beatrice anticipated before, and then the clean air gets out of the machine by an outlet. Of course, the design phase of the machine needed to be split into several parts. It was impossible to design the machine out of sudden immediately. So we decided to start with the first step of a 3 phases design methodology, which was about optimizing the impeller. The impeller is in fact the core, the key component of our system. And as we don't buy the impeller by a supplier, but we design by, let's say, we have a personal design of the impeller in order to meet the autonomy and the electrical, let's say, low consumption of the machine. We used massively SimScale for designing the impeller. Then the second stage was about to optimize the whole geometry of the machine. And then the third stage was to use SimScale again for developing the modular accessory, like, for example, an electric drum, a flexible pipe, and so many more. Let's start with the first stage. In order to optimize the impeller, we used a kind of wind tunnel approach. So we basically put the different shapes of the impellers into a simple cylinder, isolating it from the whole system. And instead of going for trial and errors, because as you can imagine, improving a certain component, even with CFD, could end up into running so many cases without never finding an optimum, we use the Taguchi method and we apply it through SimScale simulation. How does the Taguchi method works? Basically, you can define a certain number of control factors for your system. In our case, it's just the impeller. So it's a relatively simple system, which has, for example, as control factors, the internal diameter of the impeller, the outer diameter of the impeller, the shape of the blades, so the sections, the angles, the twist of the blades, the camber of the blades, and so on. And each, let's say, the drawback of the system that we know, the drawback of the Taguchi method is about the high number of simulations and of analysis that each run of the method requires. So just to give you the idea, a simple problem like this one with only 8 control factors requires each time 19 design cases to be analyzed. But we also, it's not only 19, actually it's the double, because every time we needed to simulate the impeller both as a blower and as a vacuum. It's an axial impeller, which we were able to optimize by switching the counterclockwise to clockwise direction to make the function mode switch to. The Taguchi method basically returns a series of values regarding the efficiency, like the eta, the first parameter that you can see on top of the screen in the graphs, and the information about the useful power that you can see in the lower part of the graph for each separate control factor. So basically, each control factor is like a small slider, a small leverage that we can use to tune or to change the design of our machine. And we can set it up, let's say, up to 3 levels, from 1 to 3 levels each time. In this case, every time the return of the Taguchi analysis will give us the optimum configuration given those control factors and given that range of levels that we set. Of course, I would strongly encourage you, if you have any questions regarding the methodology, to ask whatever you think in the question and answer moments. So I'll go a little bit faster on the fluid dynamic approach right now. Long story short, we applied 13 iterations of the Taguchi method, which is a total of 247 simulations. And this is definitely impossible to be done without a software like SimScale that runs pretty fast, with pretty nice aligned results with realities. And thanks to this combined approach, the digital twin, we were able to obtain an impeller that started from a 20% efficiency, of course, in the wind tunnel that we designed, up to the 90% efficiency. So we were pretty much satisfied, because this is the target that we gave ourselves for the first stage. Then we entered the second stage of our design phase, which was the airflow optimization in the complete machine. So we changed time by time the shapes, the length of the pipe, for example, the sections of the pipes, for example, and so on, in order not just to optimize just the suction or the blowing, but also to perfect the cyclone effect in order the leaves to stay into the bag without being expelled from the machine itself. And we also went to the third phase, still with SimScale, analyzing the different accessories that we designed. For example, here you can see a simulation of the broom, the electric broom that perfectly fits our design. And here you can see, for example, the flexible pipe that the user can use just to reach difficult places like small angles, small corners, and so on, while both vacuuming or blowing away. Going back to SimScale, in terms of simulations done on the full system, so it's no more just the wind tunnel, but all the machine. We ran 81 simulations, and in this graph you can see for each run that we did, both the PM, which is the mechanical power absorbed at the shaft in watt, and the useful power, which basically is the power coming out from the from the force of the outlet by the airspeed. And as you can see, run by run, while the mechanical absorbed power at the shaft was quite steady, the useful power was increasing up to arriving having an actual efficiency which is 4 times higher rather than the first design that we had. So we basically are having a very high performance also compared to the other competitors, with definitely a reasonable amount of absorbed power. Of course, we didn't limit ourselves just to the simulation part. So, as I said, 81 simulations were also integrated with the manufacturing of the 3 generations of prototype. And in this graph, for example, this is a little bit our internal benchmark. The frontier of this radar graph is, let's say, the target represents the targets that we gave ourselves in order to understand where we are with the design phase. So let's say, given 100% in terms of vacuum performance, blowing performance, the weight, the filtration, the accessories, and the battery, we can say that each time the new generation was overachieving the previous one, and now we are very, very close to obtain a final generation, which will be generation 4, which will be probably the final design which we will be used for the actual POC of the system. And this was achieved actually in just 6 months, because we started using massively this approach in September 2024, and all the methodology that I described was finished in March of this year. And one more thing that I would like to add actually is that we have never been left alone by SimScale during this journey. Actually, their customer support is very strong and efficient, and they are very present. It's very simple to chat with them daily. I was having daily conversation with one of their team, and I can say that we are very, very satisfied about that. And thanks to this approach, the leaf chaos is no longer a problem.
Great. Thank you so much, Andrea and Beatrice, for these insights. Amazing. Please, as we said, post your questions about all of that for the section later. I will just give you now a brief introduction also on the AI strategy of SimScale that is kind of on top of the CAE simulation that you can run that we also saw, and that also connects nicely to the iterative work that we saw from Nantu. So to quickly dive into it, AI is used in many applications already. You know it. It's a very trendy industry. It's also a buzzword that is used everywhere. But we also see it in a sense, it's not the solution to every problem. But we at SimScale, embracing it, didn't find many problems so far where it didn't help us, right? So thinking of why it is used so much already around the world, but not that much in engineering. So as examples where it's already applied quite well is copywriting, large language models, design, coding. You know that automatic code generation is a huge topic that is working quite well with the current AI approaches. But in engineering, it's not that much the case. The reason for that is essentially in engineering right now, we have kind of this traditional workflow of coming with a CAD model, so a geometry representation of the later real product. Then there needs to be some human that does the simulation setup, consumes the simulation results as a validation. The CAD designer needs to update the CAD again, right? And this is a circle where many inefficiencies can come in. So response times from different teams, knowledge of the people at hand that are doing these jobs, and simply the fact that a lot of human effort is needed to turn these jobs around. So that is why this is a problem. There is not many universal data types available. There is no big public data set, so it's much harder for AI models to make sense or provide value in this space, right? SimScale's AI strategy wants to change that, at least in the field of providing physics information, so what we so far call simulation. And I'll show you quickly how we want to do this. So essentially, we already talked about Cloud CAE, how it enables and makes simulation accessible essentially to engineers, but that is in that sense the traditional world of running simulations. Physics AI is what we call the AI support to get these physical results that you usually would be doing via simulation or in real world via physical testing. And what this means is that we provide simulation results to an AI model, so a graph neural network, that then provides simulation results back based on that AI model. That can be either foundation models, so that there's a lot of data available for a certain application type, so that you can actually predict simulation results on a completely new product, right? Or it can be custom models where you actually train data specifically around a product or based on past product lines or past versions of the product, and to then iterate faster on this custom model. The second part is what we will be showing about the leaf blower AI model. What's important is that always you can retrain these models, and retrain means essentially that you can expand the scope of it, or you can expand the design space where they apply accurately. So if you trained a model for a certain design space, and then you're thinking about maybe adding more impeller blades or add a new parameter on top of it, you can actually fill these weak spots in the model without needing to start from scratch. So that is quite nice. And you can couple AI models to optimization loops or other quite nice workflows in engineering as well. The second thing that we are doing is engineering AI. We call that essentially an agent that helps you really set up your application, so that we get not just the response time for simulation down via physics AI, but that you also get the simulation setup time and the setup specifically at the first time really down. So this is essentially like a chat where you enter what you want to do, that understands from the geometry that you upload what the geometry might be, where you can ask questions, what type of simulation you need to run to get a certain output that you're looking for, and that helps you essentially get finally really to the finished simulation and the result that you want to see. We will focus today on the physics AI part, but there's a lot of content from SimScale already out there on the engineering AI. So if you're interested in that topic, obviously visit our webpage and dive deeper for that as well. Both of them together and adding the traditional Cloud CAE that then serves more as a validational framework, rather like physical testing, we get to essentially a point where you can really decrease your simulation lead times, where you can test extensively, optimize a lot, and obviously out of that you get higher product performance. It becomes feasible to invest so much into optimization. You do not need to stop after a certain amount of iterations and get all of the benefits that you require to design great products. So for today's application example that I will also show you in the live demo, I want to introduce you to two different ways of how we can set up now these custom AI models. One is that you actually train a model based on synthetic data. That means you're thinking about the design space that you want to really evaluate and dive deep into, and then you set up an optimized parameter distribution, so a certain set of values for each parameter that you want to simulate so that you can later on with the AI model explore it the best way. So that is really that you target the simulations to train the AI model. It's specifically great if you have an application where you want to explore the design space really deeply. So you want to change many of those parameters and want to find the real optimum, because then it's worth running these simulations to produce the training data. And obviously, as you can do it on our cloud platform, the training data can be produced all in parallel, so the time is not actually a big factor for that initially. And then obviously you can evaluate your designs rather in seconds than in hours or minutes as for traditional CAE. For our example that you can see here, we just applied various parameters, so like geometrical parameters as blade numbers and height, but also some simulation setup parameters as the flow rate. The second way how you can do it is using existing data that you already have from the past and train a model based on that. So you can actually use past design iterations to train a model and then predict fast and iterate faster essentially in the future. We saw it, I think Andrea called it massive iterations that they did to produce better products. Now we can make use of this past information to become faster essentially in predicting physics via the AI model. Obviously, if now there's new things that come up in the next generation of the product, you can also again fill the weak spots in the parameter space by adding some simulations and also use that for training the model. But you can really use that base, and you can over time add experience and value to the models that you have. And that is also just your models, right? As a customer from SimScale, obviously your data is all yours, and that also relates to your AI model. So everything is contained for you, and you can really build up great knowledge and great value from these models. Again, same as with the synthetic data, then you can evaluate your designs in seconds. From the example we saw before, right, I just extracted here a couple of different variations of the impeller that was changed and updated here to show kind of what types of iterations were done. And then we will now show kind of how to predict on an unseen variation of that in the live demo. Great. How does it really work? So a quick deep dive into how AI training works and how AI model generation works. For the leaf blower here with the synthetic data, we set up first a simulation compressible flow. I'll show it on the platform later. We decided for 3 parameters: number of blades, blade height, and impeller RPM, and we ran all configurations then in parallel in about 1 hour. I think initially we ran about 25 simulations for that one. Then we do an AI model generation and deploy. So we create this graph neural network. We wait for the training loss and validation loss curves to come down. You can obviously specify certain parameters around that, but we also try to automate as much as possible so that kind of the core knowledge around how to train AI models, etc., can be provided by SimScale, but we obviously provide some parameters that you can also control. And I mentioned already that they are easily expandable later on. And as then a last step, you can predict your results on the platform. It's important to note, though, that by default, we always exclude part of the simulations that are available for training and do not use them for the training set, but we call it a test set, and we validate the AI model based on the test set. So essentially, we look at how good does the AI model predict the results on this test set where we actually do know the simulation result, but the AI model did not see them before, so they were not used to train it. And then essentially, you can see here, obviously, on that graph, if the AI predicted velocity would be as good as the simulated velocity, it would be exactly on this line in the middle, but we can predict quite close for most of the setups. If you have now outliers, you can think about running maybe a few simulations to essentially extend that parameter space and also be more accurate around these variations. Great, and you can see here one example of then a 3D field of the prediction, but you can also predict scalars and other quantities as well. Great, so that brings us to our live demo. I will now jump out of the slide deck, and I opened up a couple of SimScale projects for this. So I will first start with now the leaf blower that you saw from SimScale before. This is already the flow region of the leaf blower. Let me maybe hide a few faces for you so that we can, that we can look inside. Also hide here the rotating zone of the impeller. And now you can see this impeller that was variated in the skiff animation beforehand. You see here a lot of different simulations that were executed. All of those essentially have the parameter space, or kind of the parameter values in the name. So we have here 3 blades, the height is 0, the RPM is 13,000. And we have here all of the simulations that were used for the training. I excluded here the simulations that were used for the test set. We will look in a second at one of these. So it would be the 7 blades height, 14,000 RPM that was not used for the training set. But that was essentially, this is created via the API. So you can run all of these simulations quite easily, but you can also later on obviously explore them on the platform. Here we now have the 7 blades height 0 millimeter that I brought into this new project and also simulated so that we can compare results. But I will now show you essentially how I can predict the results with AI for this model. So first, I will go over here to the simulation setup. It's again the same as before, right? So we have here this leaf blower, we have the channel, and we have on the back side the impeller. And now I chose air as a material, a pressure inlet and a pressure outlet, so both atmospheric pressure on in and outlet. And then the flow is driven here by an MRF zone, so a rotating zone that rotates at these 14,000 RPM. So that is really kind of the whole simulation setup that was used. We used a mesh with 6 million cells in this run and completed the simulation. As you can see here down there, we have the simulation results down here. Instead of now looking at the simulation results though, I will now select here on top the AI preview of this. And now I have here 2 AI models available. One is the one that we trained on the Nantu data. One is our synthetic leaf blower. So I will now select this. And what now happens in the back essentially is that this new geometry version that I used here with the 7 blades and a certain, so the height 0 simply means that the height of the blade was not reduced, that this version of the CAD model is now presented to the AI model, and it now tries to predict the results that I'm interested in onto this model. And to make it easier to see, I made a cut plot of this, so I defined this during the AI model setup, but now we see the velocity magnitude of this. The simulation run, as I said, with meshing takes about an hour. Here we had several seconds until we essentially get a 3D result inside of the viewer, and we also get down here a result control that I defined previously, and that is the UI, so the direction of the flow, the outlet velocity here on this side, which is minus 1.29 meter per second. We can now, similar as in our post-processing for CAE results, choose different fields. So we can, for example, also choose this Y component that we see what produced this color result here on the right-hand side. And then I can also show you the pressure field afterwards. So this was velocity in Y direction. And let's also switch to pressure. So after loading the result first, also the prediction then for the different fields rather means loading now these results, so that goes even faster. So now we can take a look at the pressure field as well, right? So the same that is seen here now from the AI model, obviously I can do by running this simulation. I would even recommend, if you're using such an AI model, that you do run actually a validation simulation in the end on the model that you decided to use, right? So here with the same scale that I used in the AI prediction. So we would recommend you do this, but that you use really the AI prediction to make fast iterations and find the best model as soon as possible. And again, here I can, for example, change same way to velocity y, and we can use maybe statistics here to, let's not select the cutting plane, but over here the surface area. And we see that here we have an average velocity of minus 1.38. So we had minus 1.29. We used not too fine mesh, so we could even essentially provide more runs and maybe a finer discretization to the AI model to predict the velocity here even better. But we are already in a great range, I believe, to doing this. So much about the AI model from our leaf blower, the synthetic data. I will keep it now really short on the Nantu model, but I think it's a great use case to show you that what I did here was really simply copying Andreas' project that he thankfully provided for us, that we can take a peek and see if we can train a model based on this data. You see the simulation runs that were done by them in the past, right? So this was executed in January, long before we even spoke about this webinar. I think the mesh size here is about 3 million cells. Yes, exactly. And now we used all of this data. It's about 25 runs as well, I believe, to train a model as well, but left out again some runs to be test values. So I will now check one of these test data runs. So let's open up the geometry. Also maybe take a quick look at the impeller inside just by making this translucent. So here we have this rotating zone around the impeller blades. And if I now select here AI preview Analyse ML, then we will see that again, we can predict now this model as well. We did not define here result controls prior to the setup, so that we can still do, but it requires some additional effort. So we will only see the results on the outside faces of the geometry, but it's quite interesting to compare them then to the simulation results that were obtained in the past. Again, mentioning this model was not seen by the AI model. So this is a prediction on obviously an impeller that is very similar, not entirely different to what was simulated in the other iterations, but is a completely new geometry itself. Great. So here we now have the prediction. We see here now velocity magnitude at first. Here we don't have a slice plot. As I mentioned, we will only see the results now here on the outside faces. So probably the most interesting physical variable to look at now is the pressure field. Let's also load this one so that we can see how that looks for that prediction. You can already see that loading here, the results takes a bit longer. So simply the model is more complex, or if you will, in better shape to predict this simulation data. So now we see here the pressure field on the outside. I adjusted the scale again in the post-processing to see the same scale so that you can make a comparison, and loaded the simulation fields up front. Wait, so we need to quickly switch back and forth here to reload it. 1 second. And we have the result fields here as well, right? So as I said, I adjusted the scale to the same as for the AI prediction, but now switching once or twice back and forth, you already see there are slight differences, obviously, right? But in the same range, this prediction looks pretty good, right? So that is really quite helpful, as it was not, the parameter set was not optimized to do exactly this prediction, but it's really just past data that we used. And hopefully with, this is just one set, so generation 2 of this product, maybe including all of that data will really help then Nantu for further generations or other products that they might be designing in the future to make use of this and be even faster in the great product work that they are doing. With that, I would leave the live demo now, come back to the slides. And thank you for your time, the interest in Nantu and SimScale, and obviously we're now looking forward to your questions. And now Alex will wrap it up and help us get through the Q&A session. Thank you.
Lovely. Thank you very much. All right, so yeah, thank you to all of our speakers, Beatrice, Andrea, Alex today, and also, of course, thanks to the Nantu team for allowing us to play with their projects in SimScale there with the AI at the end. So we've had a few questions come in. I've been scribbling them down here on a piece of paper as well. So let's get started. We can maybe spend about 10 minutes running through these questions before we let everybody go. So let's see. Maybe we'll start with one for Nantu. So one thing you mentioned at the beginning was the physical prototyping, the cost of the physical prototyping. How did the simulation work allow you to reduce that physical prototyping effort? Maybe that one could be for Beatrice.
Here I am. Okay. Can you hear me?
Yeah, sure.
Okay, perfect. Andre, can you go for this part? Because I have some problem with the audio. I'm sorry.
Sure. The question was that
I changed it.
Yeah, you mentioned at the beginning the difficulty and the cost of physical prototyping. And once you introduce simulation into your design process, how much were you able to change your approach, and like what role did physical prototyping then take?
As I said during the presentation, so before starting using SimScale, we built actually one prototype per se, but with many variations each times. So we were changing the impeller, then we were changing the pipe, then we were changing the geometry of other components. We were going trying and errors, and the approach was actually leading nowhere. It's hard to make an estimation of the saving itself, but if you consider that we ended up building only 3 prototypes before having the 4th one, which probably with the good probability is the final one, in front of the more than 200 simulation that we performed, goes by itself that was not possible to achieve this certain level of optimization of the geometries on the components without this method, without having SimScale as a partner, because otherwise it's impossible to think about building 100 prototypes, which is still 2.5 times less than what we actually calculated. Each prototype would cost around 1,200 euros. That's the math, plain and simple. So even if you build just 10 prototypes, let's say 10 prototypes, and we are very lucky, that's at least 12,000 euros. It's probably insane, the amount of it. That's the thing. It's very difficult to make an estimation, but actually the trade-off is with the performances.
Sure.
So we are very confident on that.
Thanks. That makes sense. Then there were a couple of questions about your methodology. So one was in the once you had created an optimized impeller, did you then run that exact geometry in your complete model? And I think this has possibly been answered already, because we saw one of those geometries in the model when Alex was using it. But I think the question was asking about whether you used any approximation, like momentum sources or actuator discs or anything like that.
No. The impeller had
Always the impeller.
Otherwise, it's pointless. The problem with this kind of physical problem is that even small variations on the impellers will make a drastic change in the performance. And in this particular market, the big voice of the market is actually the autonomy of the battery. And each time you save 5 to 10 watts, it's a big deal. So you cannot go with approximation. Okay, you can save some small radius. You can let's say avoid the small features that you actually have when you print or when you mold the actual impeller. But we are talking about 0.1, 0.2 millimeters radius. So that's okay. Otherwise, all the radius are those, let's say the blade profile is exactly the blade profile that we manufactured.
Okay. And maybe what the question was asking was, like, were you using a moving reference frame to model the rotation of the impeller, or were you rotating the mesh?
No, we use the MRF function in SimScale.
Right. Yeah.
So basically, it's correct me if I'm wrong. I'm not very good at explaining technicalities, but basically there is a tool in the software that makes the user able to define a certain area in the model, and everything in terms of solid geometry inside that volume that the user defines is assumed by the software being rotating. So basically, given our pipe having a certain diameter, the impeller has a slightly smaller diameter, of course, because of tolerances. So let's say a couple of millimeters less. And so the volume has a diameter in between the diameter of the pipe and the diameter of the impeller, and the length which is a few millimeters longer than the actual side view of the impeller. So you know that everything inside rotates.
Okay. Yeah, then maybe we'll have one or two more. So quite a few questions about your modeling. One was you mentioned, I think, like 247 and 81 runs. How did you actually implement the optimization process? Like, did you do it by hand, or did you do it through the API?
Not by hand. The method that I introduced in the presentation, the Taguchi approach, is a signal to noise method based. So basically, you can imagine that each physical system has some inputs and output. In this particular case, the rotation of the impeller is the input, and the output is the actual pressure and the airspeed that you have at the outlet. Okay. And in this case, you have some control factors like those that I mentioned during the slide, but also you have some noise factors, like, for example, tolerances and imperfection of the geometry and so on. The signal to noise is exactly the same definition that you have in the electronics. It's a logarithmic ratio between the amount of the actual signal that enters, actually that exits from the system, and the noise induced by the noise factor. The approach is about maximizing the signal to noise ratio, and in this way you basically have something to measure. In our case, it's slightly more complicated because we have efficiency and useful power to be monitored, and that's two signal to noise ratios that you calculate each time, and two working modes, blowing and vacuuming. So you have actually four. So you have to make a trade-off, of course, out of them. And let's say each time that you perform an iteration, then you create a Latin square, which is a matrix which has all the levels and all the control factors for each iteration in an orthogonal way. It's an orthogonal array, very, very elementary, but it allows you the possibility to decouple each effect. Of course, under the hypothesis, purely mathematical hypothesis, that each control factor is independent. Of course, it's not. But the one that we chose, like let's say the diameter of the inner diameter is independent from the outer diameter, just saying, or the shape of the profiles of the impeller is independent from the outer diameter. It's the number of blades, it's independent again, kind of, not fully true, but kind of. So all the control factors were supposed to be independent. You make the decoupling via the signal to noise ratio, and each time the method provides the optimum set of levels for each control factors. The iteration number 2 starts reducing the window of the 3 levels of the control factors.
Sure. And so did you implement that like programmatically with a script?
Yeah, no. Unfortunately,
was that part manual?
The problem is the CAD modeling, because each model models as different geometry. So even if it's okay, let's say the impeller, yes, the impeller was actually designed with the CAD software with a script that allows me to produce for each iteration 19 impellers, just like in 5 minutes. That's okay. That's simple. So for the impeller in the windpipe, yes. But for the actual machine, when we started optimizing that, of course, it's the CAD model. You cannot fully automatize that. So you need actually to re-import the model each time.
Okay, that makes sense. Thanks. Okay, and then maybe we have time for a couple of quick questions about the AI side of things. So one, and it's a question we often get is how many simulation runs are needed to train a model like the ones that you showed, Alex?
Yeah, so that depends a bit on the parameter set that is looked into, right? So we had here just a bit about 20 runs to look at this, but we also just looked into one parameter. So if you want to vary now the flow rate, if you want to vary what Andrea told about, that they want to have kind of the blowing effect and then the vacuum effect as well, and you want to change the geometry of the impeller plus other parts, then it really becomes relevant that you add some smartness of how to create essentially this data set, so that you use some like Latin hypercube, so that you think about how you sample the data to run these simulations and get good predictions for all of these parameters. If it's just one parameters, you're probably quite well equipped with about like 30 to 50 simulations, and totally on the safe side around 100 simulations in a certain design space if it doesn't differ too much, right? But if it's more parameters, it can easily become a larger data set that is needed.
Sure. And I guess a related question is, once you've got a model built, how do you sort of verify its accuracy?
Yeah, so there's different parameters. We have that in our setup tools available. I showed in the slides one example of kind of such a loss function. There's different parameters that you can look at. You can look essentially at the error values of the test set. There's also other measures that give you an indication of how close the variation you're looking at is to your training data, and that does not give you an absolute value like exactly what the accuracy is, but the closer obviously the model you're testing is to the training set, the closer or the better the prediction gets, and you get essentially notified or warned if you're looking at a variation that is far away from what the model was trained with, and then you can again expand the set. So there's different parameters that you can use. Obviously, we try to automate this as best as we can and provide some help in understanding these parameters, so that you can again then focus more on the result evaluation side of things and get some benefits from our knowledge around these topics. But you have full control as always. We try to keep it as simple as possible, but provide the necessary expert tools as well then as advanced options in the user interface.
Great, thanks. Very briefly, I see one question we can answer very quickly is, does SimScale have an API, which I think you touched on before?
So yes, sure. That is just standard, right? So obviously, Andrea mentioned about some of the things that are then important, how to set such a case up, right? So it depends obviously on the repeatability. How do you set up the geometry? Do you have the identifiers? Often it helps then in your CAD tool to really name the faces and bodies with specific labels, as it's not always easy to replace one CAD with the other and keep all of the assignments. So these kind of things are relevant, but as we are a tool that tries to integrate and connect to as many services as possible to provide a great simulation service, it's just core of our product to have to run everything API based, and that's what we also allow others to do. So that's why we made it a public API that you can always use and run things also programmatically.
Okay, thank you very much. All right, so hopefully, we've touched on lots of the questions there. I think at least lots of the themes in the questions, but we can address those in a bit more detail after the event in full. Yeah, I think meanwhile we should close the session. And once again, thank you very much to our presenters and to Nantu for joining us today. It's been really great to see your use case and what you're doing with SimScale. Yeah, and thank you everybody for joining, and we'll see you next time.
Thank you. Bye-bye.
Thank you.
Bye.
Thank you. Bye. Thank you.